Welcome back. In the previous video you learned the following. If T is a linear transformation from Rn to Rn, then the following two statements are equivalent. T preserves the dot product between any pair of vectors, and T preserves norms of vectors and angles between vectors. Such transformations are called orthogonal transformations. Examples are rotations and reflections, which play an important role in computer graphics. Since orthogonal transformations are quite special, you can expect that their standard matrices have special properties as well. You will see in this video that this is indeed the case. Let's call the standard matrix U. Then the following is true. The columns of U are mutually orthogonal and have norm 1. Said differently, the columns form an orthonormal set. Furthermore, the inverse of U is equal to the transpose of U. In fact, all four statements on the slide are equivalent. The standard matrix of an orthogonal transformation is called an orthogonal matrix, so the last two statements give characterizations of orthogonal matrices. Before I prove the theorem, let's look at an example. The rotation r in the plane around the origin counterclockwise by an angle alpha. As you know, the columns of U are the rotations of the standard basis vectors e1 and e2. The rotation of e1 is the vector cosine alpha sine alpha. The rotation of e2 is minus sine alpha cosine alpha. This gives the standard matrix. Let's check the statements in the theorem. First, the columns should form an orthonormal set. Let's call the columns u1 and u2. The norm of u1 is indeed 1, and so is the norm of u2. The dot product between the columns is 0, as you can check yourself. So indeed the columns form an orthonormal set. Now let's look at the inverse. The inverse of U is a rotation by an angle of minus alpha. We can rewrite this to the following matrix. You see that this is precisely the transpose of U. This was just an example to illustrate the theorem. Now let's prove it. We already know that the first two statements are equivalent. I will show that 2 implies 3, 3 implies 4, and 4 implies 1. First, from 2 to 3. Let T be a linear transformation that preserves angles and norms. The standard matrix U has columns Te1 to Ten. Now remember that the set E1 to En is the standard basis of Rn. This is an orthonormal set. The vectors have norm 1 and are mutually orthogonal. Since T preserves angles, the columns of U must be mutually orthogonal as well. Since T preserves norms, the columns of U must have norm 1. Hence, the columns of U form an orthonormal set as well. Statement 3 follows from statement 2. Let's move on to statements 3 and 4. I will show that U transpose times U is the identity matrix. Remember that the rows of U transpose are precisely the transposed columns of U. Calculating a matrix product comes down to taking repeated products of the rows of the first matrix with the columns of the second. You see that the first element of the first row of the product is precisely the dot product of U1 with itself. The second element in the first row is the dot product of U1 with U2. And continuing, you find that the last element in the first row is the dot product of U1 with Un. We can continue with the other rows. You see that the product matrix consists of dot products of the columns of U. We assumed that the columns of U are orthonormal. That means that in the matrix we found, all elements are 0 except those on the diagonal. Those are equal to 1. Hence, indeed, U transpose times U is the identity matrix. But since U is a square matrix, this immediately implies that U is invertible, with inverse equal to U transpose. This proves that 4 follows from 3. Now the last step. I will show that statement 4 implies statement 1. That is, if the inverse and transpose of the standard matrix are equal, then the transformation must be orthogonal. Indeed, let's look at Tx dot Ty. I have to show that this is equal to x dot y. We can rewrite it using the standard matrix U. Then we can rewrite the dot product using transposition. Using the product rule for transposition, we find this expression. Now we can use the assumption on U. Since U transpose is U inverse, U transpose and U cancel. Writing this again as dot product, we see that indeed Tx.Ty equals x.y, no matter what x and y are. This means that T is an orthogonal transformation. We have now proven the entire theorem. All 4 statements are equivalent, so each of them can be seen as characterization both of orthogonal transformations and orthogonal matrices. You can explore even more properties in the exercises.